Okay, this might just be the last video as far as linear algebra is concerned, except something else comes up. And here I'm still looking at advanced and applied linear algebra. So at this very advanced level, we see how linear algebra actually plays an active role in some of the things that have come to change our world. So linear algebra in networks and graphs is what we are considering here. So interestingly, on this channel, I can let me even navigate and see if I can show you that. I have a playlist on network and graph theory, or better still, graph and network theory. So if you want to understand the basic ideas of network theory and graph theory, that is the playlist for you. Okay, network and graph theory. I think it was like a year ago. Can I still see that? Network and graph theory. Um, where is it now? Network and graph. Network and graph theory. Seriously? Where is it? Okay, yeah. Graph and network theory. Yeah, is it right here? So I have 25 videos, 25 videos, starting from introduction to graphs, um, Python codes for graphs. And now that one beautiful thing about that is that I had Python codes for almost everything there. So you want to check that out if you're interested in graph theory. So if I remember at one point I had a bit of issue with my pen, so I had to write with my fingers, and that, that was a very funny experience. The writing was quite crazy on the let me try to see. I think it must have been these Dirac's and Ores theorems. Okay, I don't think it's this one. I'll locate it for sure. Let me see. Okay, could it be this? No, this is still looking nice. It's not this, it's not this. Yes, I guess it's all these ones. Oh, it's not even this. What about this? Yes, I use my fingers here. So you can see the writing is looking a bit it's somehow, but it's okay. I mean, it's clear enough for people to read. Maybe just too big or something. Yeah, I think it was this particular one. So you want to check all these things out, and okay, this one I already got my pen back or something. Yeah. So yeah, this, yeah. Okay, so I mean, if you want to check out graph and network theory, that's there for you. You want to avail yourself of the opportunity to study graph and network theory into some depth. Okay, so here we're looking at linear algebra in networks and graphs. So, and this basically talks about connections. This lesson explains how linear algebra is used to analyze networks and graphs, focusing on adjacency matrices and PageRank algorithm. Well, the PageRank algorithm is what is used in search engines, especially like when you do a Google search. So the rank algorithm is going on there, and so you can see how linear algebra plays into how we use the internet. Okay, so let's go straight and talk about graphs and networks. First of all, a graph consists of nodes. That is what you call vertices. These are objects such as web pages or people, right? So it's more like you're on Facebook. Imagine that you're on Facebook. Um, this is me right here, Emmanuel, and then I know somebody called Margaret, and then I know somebody called Olayiwola, right? So these are three different people. So I can be connected to Margaret, and then Margaret is connected to Olayiwola, and I may not be connected to Olayiwola, and I may be. So whatever. So I can be connected like that. So it's all about, so network theory is about connections, right? How people interact, how people connect. So um so a graph consists of nodes, with or vertices, that's objects such as web pages or people. So even web pages can be linked. One web page is linked to another. So you have edges or links. These are connections between nodes. So these edges now. So this is a connection now. Whatever. however that connection. Somebody sends a friend request and then somebody accepts, then a connection is established. But if there's no connection, that so I mean they are just in silos, so to speak. Or maybe through the fact that Margaret is connected to both Emmanuel and Olaiwola, then someday we can both get connected. So those are the edges that make those connections possible in that case. Then we can have graphs. On the other, graphs can be undirected. In that case, now edges go both ways, and then they can be directed where edges go only in one direction. Okay, so um, so an undirected graph, a very good example of a graph being undirected is, you just have this connection. So you can have both way connection. So it's more like Emmanuel is Margaret's friend, Margaret is Emmanuel's friend, right? Emmanuel is Ola's friend, Ola is Emmanuel's friend. So and you have two-way friendship in both. I mean, it's interesting to know that sometimes it can be someone's friend and the person is not your friend. All that. So um, graphs can be directed. In that case, edges go in one direction. So undirected graph, the edges just go on like that. But in a directed graph now, imagine say Emmanuel, so Margaret, and then Olaiwola, right? So in a directed graph, Emmanuel is connected to Margaret strictly in that direction. Then Margaret is connected to Ola strictly in that direction. Then Ola is connected to Emmanuel. It's like a kind of one-way thing, right? It's kind of one-way thing like this. So that's a directed graph. So this is directed and undirected. Okay. So I think a very good example of that will be maybe on X, former Twitter. Yeah, you follow someone and the person doesn't follow you, right? So things like that can be considered. Now we have adjacency matrices, which are well explained in the playlist on graph and network theory. Suppose a graph has n nodes, like in the case of Emmanuel, Margaret, and all that, has three nodes. So its adjacency matrix A is an n by n matrix defined as Aij. So is one if there's an edge from node I to J. So if there's an edge from between I to J, then the adjacency, the value is one. It is zero if there's no edge. So for instance, let me see if I can make that possible. In this case now, so we're talking about adjacency matrix. Here we have Emmanuel, Margaret, Ola. Okay, we can have this now. We have Emmanuel, Margaret, Ola. So in this case now, if you follow this particular example, um, so from Emmanuel to Margaret, there's a connection. That's one. From Margaret to Ola, there's a connection. That's one. From Ola to Emmanuel, there's a connection. That's one. So every other thing is zero, like this. So that's the adjacency matrix for this particular directed graph. That's what that means. So if there's a connection, then you say the value in that case would be one, like that. That's the adjacency matrix. So for weighted graphs, the value represents the edge weight. So let's look at a directed graph, for instance. Imagine that consider three nodes A, B, C with edges A to B, A to C, B to C, C to A, right? That is, there's a connection from A to B, from A to C, from B to C, from C to A. So you can then label A to be um A is 1, 2, 3, for instance. So to build the matrix now so rows represent nodes, as we know. Rows represent nodes, and then columns represent rows represent from nodes and column represent two nodes. So the adjacency matrix can be this now. So because here now you have 1, 2, 3 on the row, 1, 2, 3 on the column. So it's more like there's connection from, so A is 1, B is 2, C is 3. There's connection from 1 to 2. All right. So this is from 1 to 2. That the value there is 1. There's connection from 1 to 3. That's also 1 right here. Next, there's connection from 2 to 3. That's row 2. That's 2, 3 here. That's 1. There's connection from 3 to 1. That's 3, row 3, 1. So every other thing will be 0 in short. So in that case now, the interpretation is that row 1, which is row 1, A goes to, for in row 1, there's connection from A to B and from A to C. on row two, there's connection from B to C. Okay, in row three, we have a connection between C and A. That's what adjacency matrix looks like. Then we talk about the idea of undirected graphs. For undirected graphs, A is equal to A transpose, meaning that there's connection in both directions. So it's like so there's a so yeah, if you are connected to me, I'm connected to you. That's basically what that is about. And that is why the transpose of the adjacency matrix is equal to the adjacency matrix itself. So the adjacency matrix is symmetric. So if A is connected to B, then B is connected to it. That's the idea of undirected graphs. So and that is what I've shown here in this picture. Um, talking about directed and undirected graph. So for directed graph, A B goes to A goes to C, C goes to B. But for undirected graph, well, I should have shown the arrow in both ways so that everybody is connected to everybody. Like A goes to B, B goes to A goes to C, C goes to A, C goes to B, B goes to C. And that is why the transpose of the adjacency matrix will be symmetric like that because so the adjacency matrix is equal to its transpose. Then we talk about the degree of nodes. The degree of nodes. So we have out degree of node 1. So out degree I is summation of j aij. So out degree means how many from A from node I, how many points are reached from A. Yeah, that's the idea of out degree. So in this case now, let's look at a scenario where we have so again, A, M, O. So let's say A reaches M, A reaches O. Okay. So, yeah. And then, so in this case now we can say that D, the degree of A is 2 because it reaches, A reaches M and O in this case now. Okay, let's even say it is uh, yeah, let's even say it is an undirected graph. So in this case, the degree of M, how many places does M reach? Just one. The degree of O, the O reaches only A. Okay, that's the idea. So the out degree. So, but for in degree now, how many points reaches have so for A, for instance, now for in degree, that is how many points reach A. In this case, now that will be 2 also. Okay, that'll be 2. But how many points reach M and O? Also 1, like that. So we have in degree and out degree. So in degree of node I is in degree. So that's from aij now. So for out degree I, so summation of all j's such that you have aij, that is moving from I to j. So how many j's do you have? Then in degree of node, in degree I of node I is summation of all j's such that j goes to comes back to I. So how many points reaches I? That's in degree. Then out degree is how many points does I reach? That's the idea. For example, here you have in this place now. So if you talk about A is the first one. So A reaches B and C. So the out degree is 2. Then for B reaches only 1. The out degree is 1. Then C reaches only 1. The out degree is also 1. So talking about the in degrees, how many points are reached by A? This is A here. Okay, this is A. So how many points are reached by A? So this is A. In this case, now the in degrees for A. So, this is A down here now. So I think you read that across the column. So the in degree of A is 1. Okay. So for our degree, you look at the row. For in degree, you look at the column. So only this point is reached by A. Only this point reaches A. So um A, B, C. By A. Okay, this is A right here. So that is this one. So C reaches A right here. But on the other hand, for B, you can look at the column. 1 reaches B. That's all that B has. For C now, C is reached by both A and B. That's why the in degrees are 2. I guess maybe what I did, may not be perfect, but this is a better way to explain. So if you want to look at the out degrees, you look across the rows. If you want to look at the in degrees, look across the columns. So for out degrees for A, you have 1, 2. Then for R degrees for B, you have only one. For R degree for C, you have only one. For in degrees, you read across the columns. So in degree for A, that's one. For B, another one. For C, that's two. So I think that's one thing to establish. Like out degrees, look at the rows. In degrees, look at the columns. Then we have parts using matrix powers. So we can have parts using matrix powers. Matrix powers count parts. So A k sub ij is equal to the number of parts of length k from node I to node j. So this allows us to analyze reachability and connectivity. So I dealt with all of these things very well in the playlist on graph and network theory. So imagine you want to compute a squared. That's a dot a. So a squared is uh if I think it's the same A we had before. So you have 101, 100, 0, 1, 1. So interpretation is that A squared 1, 3 is 1. That is for A squared now, 1 reaching 3. That's 1 reaching 3. Uh 1 reaching 3 is 1. Yeah. So that's 1, 3 here. So there's one path of length 2 from A to C. So there's one path of length 2 from A to C. So this is A now. From A to C, you reach here and then you reach here. Okay. So, introduction to PageRank, which is another application now. PageRank measures node importance. Okay, it measures node importance. It measures the importance of a particular maybe site or something. So a node is important if important nodes link to it. So how do you know if why do we call some people influencers today? They are influencers because they have many people following them. So as someone who has a lot of people following them, it can be said to be important, right? So a node is important if important nodes link to them. And of course, not all links have equal value. So all kinds of links can come to a person, but how weighty are those links, right? So, and that's why PageRank is useful. So there are different models we use in PageRank. So random software model is one thing. So imagine a person who starts on a random page, then clicks links randomly, sometimes jumps to a random page. So the long-term probability of being on each page is its PageRank. So what is the probability you are going to reach a particular page, randomly? That is the idea of PageRank. And then we go to talk about a transition matrix. From adjacency matrix A, we build a matrix M. If node J has K outgoing links, then we say Mij is 1 over K if J goes to I. All right. Each column of M then sums to 1. Of course, in this transition matrix, we have that kind of thing. So imagine the adjacency matrix right here. So for out degrees, we say for out degrees, you look at the rows. So this is for A2, B1, C1 also. Those are the out degrees. Then the transition matrix here would have to be like this. So for the transition matrix, you have 0, 0, 1. Then this is half 0, 0, half 0, 0, like that for the transition matrix given. So to, to now rank the vector, to rank a vector, what do you do? So let R be R1, R2, R3, where R is the importance of nodi. So we want R to be MR. This is an eigenvector equation right here. So R is the eigenvector with eigenvalue 1, right? Um, so this is an eigenvector equation as you can see. So, then we can say R minus MR equals 0 or something. And then we can find the absolute value of M minus I in that case. So then we have the damping factor. To avoid dead ends, we use the damping factor, D, usually 0.85. So we have R equals D MR plus 1 minus D 1 over NI. Interpretation with probability D, you can follow a particular link. So with probability 1 minus D, you can jump randomly. Okay. Then we have power at iteration algorithm. So you can initialize, you have R of 0 equals 1 over N, all like equal possibility of 1 over N. And then you can repeat, you have R K plus 1, that's DMR K plus 1 minus DV. Then stop where RK converges. So this computes PageRank numerically. A very good example. Imagine the matrix, the transition matrix is 0, 0, 1, half 0, 0, half, half, 1, 0. Okay. So along the columns, right? If you add things up, you just get 1 all the way. So, and you have initial vector of 1/3 all the way, just like we had that 1, 1, 1 and 1 by n, 1 by n, so that everything adds up to 1. So the first iteration, we have M multiplied by R0, this M multiplied by this now. So it's more like 0, 0, 1 times this. You have 1 over 3 up here. Then next you have half 0, 0 multiplied by this. So you have 1 over 6 somewhere. Then lastly, you have half 10 multiplied by this. That's half times this 1 over 6 plus 1 over 3. So that's 1 over 6 plus 3 over 6. That's 1 over 6 plus 1 plus 2 over 6. That's 3 over 6, which is half. And that's what you have here. So MR0 is 1 over 3, 1 over 6, 1 over 2. And then if you let D be 0.85, and then you use the formula, so you have R1 is 0.85 MR naught, which we already computed here, plus 0.15 into the original thing. So if you put that, the first iteration gives 0.333, 0.19 to 0.7475. So at the end of the day, so if you iterate continuously, after many iterations, you discover that is approximately 0.36, 0.19, and 0.45. In this case, now this is ABC. So from all these weights, you can see the ranking can be such that the website C has higher weight, is ranked higher than A, and A ranks higher than B. So in the right order, C is higher than A is higher than B. So node C is the most important node in this case, right? So linear algebra view in this whole matter now. So links can be represented by matrices, and the importance can be represented by a vector. Then you can update by multiplication. Stability can be given by eigenvectors, and convergence can be represented by spectral theory. So PageRank is fundamentally linear algebra system from all of these things you've been saying. In summary, we can say that for adjacency matrices convert graphs to matrices, and they store connectivity, enable computation, and matrix powers count parts. So for PageRank then, PageRank measures long-term visit probability, uses eigenvectors computed by iteration, and includes random teleportation. And then the key idea is now graphs become matrices, movement becomes multiplication, importance becomes eigenvectors, and ranking becomes steady state behavior. So we see how linear algebra plays into networks and graphs. So we have some practice problems you want to try your hands on here. So just like we saw the other time, you can actually make an adjacency matrix construction out of this. So you have a directed graph has nodes A, B, C, D with edges this. So label the nodes 1 to 4, then construct the adjacency matrix. Then state whether the matrix is strongly connected, all that. Then point two, you have a undirected graph. An undirected graph has edges. This write the adjacency matrix. So that means A to B, B to A to C, C to A, B to D, D to C, D to B, C to D, D to C, like that. So you have back and forth like that, such that there's symmetry. Then in degree and out degree, find out the out degree of each node. Out degree, you go across the rows. So for A, that's 2. For B, that's 1. For C, that's 2. For D, that's 0. Okay. The in degree, you read across the rows. For A, that's 1. For B, that's 1. For C, that's 1. For D, that's 2. Okay. Identify any sinkholes. Of course, I think um so I think this D may just be may represent the idea of a sinkhole. All right, that's what I think. I'm trying to see in degree, out degree. Yeah. So this 0, 0, 0 we have here is a possibility of having a sinkhole, I want to think. So parts using matrix power, so you can you can compute a squared and then you interpret a squared 1, 3. Find a number of length 3 parts from node 2 to 1, 2 to node 1. Then transition matrix construction, you have this compute the out degree of each node, construct the transition matrix M, verify that each column sums to 1. Then eigenvector and interpretation, like what we did before, show that M is stochastic, verify this is an eigenvector, explain its meaning in PageRank. Then 7, PageRank iteration. So you have all of this. You want to compute R1, R2, comment on convergence. Then damping effect. Consider a PageRank system with n equals 4 nodes and d is 0.9. Write the teleportation vector, write the full PageRank update equation and all that. Then you have sync nodes, and of course you have some kind of conceptual analysis. So yeah, you want to try your hands on this and see uh how how well you understand the ideas. If there's any problem you're not able to handle and you want me to solve, you can tell me in the comments, either on Facebook or on YouTube. Okay, with this, I come to the end of this very interesting video about linear algebra in networks and graphics. And of course, that marks the end of this set of 4 videos on applied and advanced linear algebra. And by extension, the end of the linear algebra playlist. It's been an eventful journey making this 43 videos as far as for linear algebra. So I had a very nice time making the videos. If something else comes up, I might just extend this. But if not, this brings it to an end. So watch out for my playlist on dynamical systems, which also bears some resemblance with some of the things we had seen here already. Okay, so let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for that. If you haven't subscribed, I wonder what you're waiting for. Why not just go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. And beyond that, you can also become a member of this channel. And to do that, right, you can just click on join. Let's say, of course, if I use my own account, it won't work. Let me use another account I have, right? So if I come here now and click on this, okay, and so I'll navigate to the this channel, and from here you can click on join, so you can see you have each bronze access, silver access, and gold access, and each of them has a particular some perks associated. So for the bronze access, you have loyalty badges next to your name in comments and live chat, priority reply to comments. So if you comment, if there are tons of comments, your comments will come up easily for me to be able to reply. Then connecting on social, we can connect on social media if you're a member. Then silver access, we can you can have early access to new videos, member shout outs. Maybe making a video, I can just shout out to you as a member. Then photos and status updates, members only videos. So some videos will be made only for members. Then access to my PDF mathematics notes. That is all this plus whatever you get, bronze access members get. Then as a gold access member, you get everything bronze access and silver access get. And in addition, you can get a one-on-one consultation on anything that interests you on this channel. Okay, so that's cool. You can avail yourself of that opportunity. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.